Okay, in this lesson we are going to talk about U substitution and how we can use U substitution to help us do more complicated integration. Before I talk about U substitution, though, I'm going to do just a quick review of the chain rule because U substitution is really a tool to help us deal with derivatives that come from using the chain rule. Okay, so I'll explain that when we get to the integration, but let's review the chain rule first. So let's say I have y equals 2x plus 3 to the fifth. Well, if I want to take the derivative of this, one thing I could do is I could multiply this out. I could raise this to the fifth, but obviously that would be extremely cumbersome. So the chain rule allows us to take the derivative without needing to do all of that multiplication. So if you remember, the derivative, dy dx, is, first I'm going to deal with the exponent. You work your way from the outside in. 5 times 2x plus 3 to the fourth, and then the derivative of the inside is 2. And I can simplify that to 10 2x plus 3 to the fourth. Okay. Let's do a couple more. Y equals 5x squared minus 7x plus 9 to the 10th. Well, you would definitely not want to multiply that out. The derivative, dy dx, is going to equal 10 times the expression to the 9th times the derivative of what's inside, which is 10x minus 7. Okay, we've also seen the chain rule used when taking the derivatives of trig functions. Maybe something as simple as y equals the sine of 6x. And for the derivative, again, you're working your way from the outside in. First, I would take the derivative of the sine function. The derivative of sine is cosine of the same thing. The argument doesn't change. Then I need to go inside and take the derivative of the argument. So that's 6 cosine 6x is my answer. Let's do one more that has a few extra steps to it. So let's say y is the cosine of, let's say, 8x cubed to the fourth. Now remember, usually this would be written like this, with the fourth power right there. But it's nice to think about it like this. You've got something to the fourth. So we've got 3 steps here. Working our way from the outside in, we're going to first have the derivative, the exponent rule, the derivative of something to the fourth, then the derivative of the cosine function, then the derivative of 8x cubed. So the derivative, dy dx, is 4 cosine 8x cubed to the third. Now the derivative of cosine is negative sine of the same thing. The argument doesn't change. And now the derivative of 8x cubed is 24, oops, that should not be an equal sign there, multiplied by 24x squared. And I can clean this all up. And I have 4 times 24, that's 96. Oh, I'm going to throw a negative sign in there. Negative 96x squared cosine cubed of 8x cubed sine of 8x cubed. All right, so why would I review derivatives before I'm about to introduce an idea about integration? Remember that differentiation and integration are inverse operations. So if I take the derivative of a function and I get this function, That means I could integrate this function and get this function, plus c, right? I would need all of this in an integral in order to get that function. All this would integrate to 6 sine x, and so on. So the U substitution gives us a really nice way to organize our work, because that can be very complicated, okay? So let's take a look at a few integration problems, and I'll explain how we're going to use U substitution to do them. Okay, so let's start with something relatively simple. Okay, so U substitution. We did some U substitution back when we were taking derivatives. I did a mini introduction, but it's much more useful here. Okay, so let's say I have the integral of 3x plus 2 to the 7th dx. Okay, so I'm going to try and simplify this expression. You know how to integrate something to the 7th, but you don't know what to do when the something is not just an x. So I'm going to rewrite this in simpler terms. So I'm going to say, oops, let me get a darker pen here. All right. There we go. Let u equal 3x plus 2. Okay, now I'm going to take the derivative of both sides of the equation. So the derivative of u, I'm going to call that du. The derivative of 3x is 3, but I need a dx also. So whatever variable you're taking the derivative of, you're going to wind up with a d something of that variable, okay? So now I'm going to go and look in my expression. This, well, that's just going to be u. And over here, the dx, well, if I look at what I have in my substitution, I can get dx alone by multiplying this whole thing, this whole expression, by a third. Then I wind up with 1/3 du equals dx. So now I'm going to rewrite my expression in u's. So I have u to the 7th, and then the dx I'm going to call 1/3 du. So dx I replaced with 1/3 du. Now remember, I told you that when you have a scalar or a constant multiplier in an integral, you can just pull that out. So this is the same thing as 1/3 the integral of u to the 7th du. And we learned how to integrate this yesterday. So this is 1/3, okay? And then u to the 7th becomes u to the 8th, and then I need a 1/8 plus c. The last step in a u substitution is to go back to your original variable. So I now need to get rid of the u, put my original expression back in, and I'm going to combine my fractions here. So I have 1/24th. U is 3x plus 2 to the 8th plus c. Okay, so again, the purpose of doing the U substitution is to take an integral and write it in simpler terms so that it's easier to integrate by making appropriate substitutions. You pick something to be u, you take the derivative of that so that you can have something that can be your dx. Now, certainly, eventually you might be able to do some of these simpler ones in your head, but for the moment, U substitution is very useful for these more complicated integrals. Okay, let's call that number 1. All right, number 2. The integral of x, 2x squared plus 3 to the 4th dx. All right, so this may look more complicated, but it's actually not any harder than our last problem. So you might think, oh, we've got something to the 4th, but then we've also got an x out here. But if you notice, if you had to guess, I hope you're going to guess that I'm going to make 2x squared plus 3 my u. So let's write that down. Let u equal 2x squared plus 3. Well, when I take the derivative of this u equation, I get du is 4x dx. Well, I have an x and a dx. Let me reorganize this. This is 2x squared plus 3 to the 4th, and I can just move my x over here. So the x dx, this is right here. To get that by itself, I'm going to multiply everything by a 4th. So I have 1/4 du is x dx. So I now have a substitution for my u right there, and I have a substitution for x dx. And I can rewrite the integral. So I have the integral of u to the 4th, and then I'm replacing x dx with 1/4 du. And again, remember, I can just pull the 1/4 out. 1/4 u to the 4th du. Well, again, here we are. We're back to an integral that we know how to find pretty easily. Oh, let's get a light on there. 1/4 u to the 4th integrates to 1/5 u to the 5th plus c. My last step, get rid of my u and put the original variable back in. So I wind up with, let's go down here, 1/20. U is 2x squared plus 3. 2x squared plus 3 to the 5th plus c. Ta-da! So, not so hard. Pick out something to be u, make a u substitution, and integrate like you knew how to before. Okay, let's do a couple more here. Okay, so let me get a new piece of paper. All right, here we go. Okay, we'll get an exciting one going here. Number 3. Okay, number 3 is the integral of y times the cube root of 3y squared minus 1 dy. Okay, so this, maybe it would be helpful if I rewrote my root as an exponent. Remember, this is the same thing as the integral of y. 3y squared minus 1 to the cube root is the same thing as a 1/3 exponent dy. Oh, there's a lot of glare there. Sorry about that. Oh, it's a little too sunny, I guess. Okay. So, okay, well, we're going to deal with this in the exact same way. We've got something to the 1/3. And if you look here, I've got a y squared, and if I make that u and take the derivative of it, I'll get a y to the first, something y to the first. So that is what we're going to do. We're going to say, let u equal 3y squared minus 1. Then if I take the derivative, du equals, this is going to be 6y dy. 6y dy. And again, I have a y dy. I can reorganize that so they're together if that's helpful. Remember, I can move things around in there. This is 3y squared minus 1 to the 1/3, and then y dy. I can put those together because that's what I'm trying to replace here. And I'm going to multiply both sides by a 6th, so I have a 6th du is y dy. Okay, so let's make the u substitution now. So this is u to the 1/3, and y dy is 1/6 du. So you could probably just pull this out the first time you write it. I'll do that now. Okay, fractional exponents. Let's integrate this fractional exponent. So I have 1/6 times u to the 1/3. When you integrate that, you need to add 1 to the exponent. So I'm adding, to get my new exponent, 1/3 plus 1, or 1/3 plus 3/3. So my new exponent is going to be 4/3, and then I need to multiply by 3/4, the reciprocal of that, plus c. So what do I wind up with? 3 over 24, which is just 1 over 8, 1/8. U to the 4/3. Let's get rid of our u, put the original expression back in. 3y squared minus 1 to the 4/3 plus c. See, it looked very complicated at the beginning, but it's really not. Pick something to be your u, take the derivative of that, substitute, get rid of the original variable and put your u's back in, creating a simple integration, and then integrate, and lastly, go back to your original variable. Okay, one last problem. One last one, and then you will be all set and ready to do your own u substitution. All right, here we go. Problem number 4. Number 4. Okay. The integral of x cubed over, let's say, 1 minus 2x to the 4th, let's say to the 2/5 dx. Okay, so when I look at this expression, I see I've got something raised, an expression raised to a power. And then when I look at that expression, I see that has an x to the 4th, so I know its derivative will have an x cubed. Now, I think it might be helpful to rewrite this expression so that I don't have a fraction. So let's rewrite this. Instead of writing this in the denominator, we will rewrite this as 1 minus 2x to the 4th, and my 2/5 exponent is going to become a negative 2/5. And then I have x cubed dx. All right, well, what is my u going to be? My u is going to be 1 minus 2x to the 4th. So this is going to be my u, and then my du, let's take the derivative of this, is going to be negative 8x cubed dx. So you can see I have an x cubed dx. I'm going to get that by itself by multiplying both sides by negative 1/8. So negative, oh, I don't really need a parenthesis there. Let's get rid of that. Negative 1/8 du equals x cubed dx. Okay, we are all set to do a U substitution. All right, here we go. The integral of u to the negative 2/5, and then I have a negative 1/8 du. I am just going to go right ahead and put the negative 1/8 there. I've been doing an extra step and pulling it out after I write the integral, but you can just pull it out right now. So we are ready to integrate negative 1/8 times. Okay. Integrating u to the negative 2/5. I have to add 1. So I have to add 5/5 to that. So that is going to give me negative 2 plus 5 is 3/5. U to the 3/5. So that means I need to multiply by the reciprocal of my new exponent. I need a 5/3 out here. Plus c, don't forget my plus c. And we are at the last step, which is putting in our original variable, getting rid of the u. U is 1 minus 2x to the 4th. So my final answer is negative 5 over 24, 1 minus 2x to the 4th to the 3/5 plus c. All right, so now you know you can take a really complicated expression and integrate it by doing a U substitution to make the expression much simpler and into something that is easy to integrate, and then lastly put the original variable back in. All right, so you are all ready to work on an assignment for U substitution.